All right, fair enough. So tonight we are talking about, actually tonight's a double header. So tonight we're talking about computer engineering for the first 50 minutes or so. We'll take a break and then we're going to come back and we're going to talk about some additional material stuff and some biomaterials. I shifted some stuff around next week. So next week, my sister, she's a doctor, like a medical doctor. She will be in to help us do our cancer therapy and cancer treatment discussion, which will be next week. So I'm excited about that. Usually we do it after this, but I wanted to move it around so that she could come in and teach because she knows a lot more firsthand knowledge about what's going on with new engineered cancer treatments. Okay, so without further ado, let's go into our computer engineering discussion. So real quick, show of hands. Who here thinks that they want to be a computer engineer or software engineer of some sort? Maybe? Does anybody just want to go design computer games? Does anybody just want to go play computer games? All right, fair enough. That's I think what a lot of people who want to go into game design realize is that they really just wanted to play video games, right? So, all right. So the first, and so I want to be very clear, we're not going to learn how to code anything tonight. Why would the main reason be that we're not going to learn how to code anything? But it's just because not CS. But the other thing is, right? I took C++ when I was in school. There's now C++, there's other things, right? By the time you guys get out, you're going to be learning multiple different coding languages. There's no point in going through that. Plus, you guys wouldn't be able to do that in an hour anyway. Instead, we're going to talk about fundamentally how computers work and why those computer languages work. So everything starts off with binary logic, right? I'm sure you guys have all heard of binary at one point in another, right? What is binary? Ones and zeros, right? So binary logic in of itself allows computers to make extremely complicated decisions or perform complex calculations, all based on a series of relatively simple inputs. In binary logic, I know we think of it as ones and zeros because that's in the modern day what it is, but really in binary logic, we consider things to be true and false. Okay? For the purpose of this class and pretty much everything that you're going to be talking about, true is 1, false is 0. Okay? That's just the way it works. So I said that's the convention in this course. You will also sometimes, if you like, actually philosophy students will take a logic course, or they will take multiple logic courses, and they're actually talking about the same type of thing. Sometimes this is called Boolean algebra. You may hear it like that. It really just goes back to 1850s, the guy who fundamentally developed it. George Boole. So a little history knowledge there. Okay, so binary logic permits 3 and only 3, that's important, 3 and only 3 operations to be performed. These are and, or, and not. So and operation is pretty simple. If I have 2 statements with an and they're both true, then the statement is true. So what it means is true and true is what? True. True and true is true. True and false is what? False. False and false is what? Right. So you have to have both true to be there. Alternatively, or is either of them. Right? So if I have true or false, what is my statement? It's true. If I have true and true, true or true, it is true. If I have true or false, it is true. If I have false or true, it is true. And if I have false or false, it is false. Very good. And then we have the weird one, which is not. So if I have true not, that is false. If I have false not, that is true. Right? So the easiest way to think about that is it's a flip. Okay? It's a flip of whatever the statement is. So if we want to put this in terms of ones and zeros, if I have 1 and 1, what's my statement equal to? True, or 1, right? For both, I mean, they're interchangeable. You guys are on top of it, exactly. 0 or 0, is false or 0. Very good. And 0 not is 1 or true. Very, very good. Okay? So while simple, like again, you guys got it. It's down, right? You guys now have it. You're experts. Okay? But while simple, these operations can be used alone or in combination to express any imaginable logic statement. One of the fundamental conditions in binary logic is the if-then statement. What this means is if something is true, then do something else. Who's used an if-then statement in Excel? Or Google Sheets or whatever, right, in a spreadsheet? Has anybody done an if-then, right? Absolutely, yeah. You can do it all the time, right? So, yeah. So one of the things we do all the time at work is if we're looking at a string of data set and you say, well, we only want the data that's below a certain value, right? Let's say you have 1,000 lines. You can write a formula that says if less than value, say good or bad, or if it fails, say or bad, and then what you do is you filter in Excel based on the good data and you pull out only the good data, right? That's a very simple example, right? If-then statements are the bread and butter of everything in computer programming, okay? So again, fundamentally it states that if a statement has a certain value, then another related condition called the logic statement has some particular value, right? So for an example, here I have, if a person is older than 16, but not older than 25, in other words, saying if they're between 16 and 25, right? If a person is older than 16, but not older than 25, or if they've had an accident, they must pay higher car insurance premiums. So we could very easily go and program a statement or program a logic statement where we said, all right, let's let variable x equal our statement that the person has to pay higher money for car insurance, right? The reason I've chosen this one is because this is very relevant to you guys. You guys cost a ton for your parents to insure, right? The person must pay for higher car insurance premium as our statement x. And then we let variable a equal person older than 16. Variable b is person older than 26. And c, the person has had an accident. And then we can represent that in the statement below. X equals a, what's the dot? What's the dot? And, very good. B, what's that little apostrophe above the B? That's not, very good. And then what's the plus sign mean? Or. All right, so here we have A and B not or C. All right, so let's yeah, exactly. So we have to kind of dive into this one to get it, and we'll start working through it. All right. So you drive, right? It's not a logic statement, yes or no? Okay. And how old are you?
16.
Okay, you are 16. So if we were doing this on you, what would your value for variable a be? You are older than 16 because you're multiple days older than 16, right? Okay, so you are true or 1. The person is older than 26. What is your value for B? Okay, false. Very good. And these are the raw values. These are not in the formula, right? And the reason I say that is because what do we have to do to her false? We have to not her false, right? And then the person has had an accident. Have you had an accident? No. So you are false. Okay? So what we have in our statement, we have x equals true and not false, or true, right? So true and not false is what? What's not false equal to? True. So we have true and true, which is true, and we have true or true, which is true. So that means that x equals true, which means that it is true that you have to pay higher car insurance. C is not false because, oh wait, you have had an accident. Yeah. Oh yeah, it's an or. Yeah, sorry, it's an or. So yeah, sorry, it's yes, you're right. It's true and true, which is true, and then it's true or false, which is true, right? Yes, you have to pay the higher insurance. All right, so let's do another example, right, without picking on anybody in the class, right? But if we apply this to a 20-year-old driver who's accident-free, A is 1, or true, B is 0, and C is 0. So if we plug it into our formula, just going line by line, we have 1 and, not 0, or 0, which becomes 1 and 1, or 0, 1, or 0, 1. True. You have to pay the higher car insurance. Any questions? Like I said, pretty much the best way to do this is just kind of dive into it, right? Because you kind of figure it out by going. Okay, so any questions? All right. So if you could please turn to page 49 in your manual, we are going to write a program. We are going to write a program to, we are going to program our thermostat at home, in your house. Okay? So let's consider the logic used by the thermostat in your house. Turn the heat on if the interior temperature is below the set point, and when the exterior temperature is not above the set point. So let's think about that fundamentally of why we would want to program our thermostat to do that, right? If it's too cold inside, we're going to turn the heat on. But we're not going to turn the heat on if it's warmer outside than it is inside. And why is that? The house is eventually going to warm up and you don't want to waste the energy, right? All right, so what we're going to do is we're going to evaluate this for an internal house temperature 75, an internal set point of 80, which your dad would probably die over, right? Way too warm. But internal house temperature 75, set point of 80, and an exterior temperature of 60. So where are we going to start? What's the first thing we're going to do? Assign variables. Perfect. So what do we want to assign for our internal? Let's just use ABCs. How's that? All right, so let's say A for internal temperature, B for our set point, and C for our exterior temperature. Okay? And you can also simplify that by just using the logic statements. A is the internal temperatures below, right? Because it has to be a true-false statement, right? So if we say A, internal temperature is below the set point, what is the value in this situation of A? So that means that A is what value? What's that? True. And why is it true? 75 is less than 80, so A is true. And then we have statement B, which is exterior temperature is above the set point. Is the exterior temperature above the set point? No, because it's 65. Okay? So we can look at this immediately and say, okay, in this case, what needs to happen to our heat? Our heat needs to turn on, right? The house is too cold. It's too cold outside. We need to turn on the heat. Okay? So it should come down to this formula. What you're going to see is X, or our formal statement, equals A and B naught, right? And why is it B naught? Because you want to say, you're just going to say the success criteria is that it is above, right? So say if it is above, we can say if it is above, we can not that, meaning it's not above. Okay? So in that case, we have A, which is we're below, and we are not above, equals our statement. So let's go ahead and plug that in, because we already said that our heat's going to turn on, right? So we have A and B naught, which is 1 times 0 naught. There's not times, sorry, 1 and 0 naught. 1 and 1, which equals 1, which means the heater will turn on. Clear as mud? All right. All right, now you guys will have noticed in the two previous examples that we had different orders of operations, right? We had multiple operations in there. Just like doing normal math, you will notice that the order in which we evaluate it matters. So there is an order of operations to this as well. All nots are done first. Then and is done from left to right. And then or are evaluated. And right there, up there, it says from the right, and that should be like from left to right, is what that should actually say. Okay, so just as you would do in normal math, different order of operations can mess up your output. All right, so one of the easiest ways to go through our logic statements is by using something called a truth table. So a truth table is really just building all possible outputs of a given logic statement. So for example, here on the left, if we were to look at this table, the AND truth table, we have input of A, we have input of B, and then we have the output of A and B. And this is what we already talked about, right? If we have false and false, it's false. False and true is. True and false is. And true is true, right? So what we've done there is you've done all of your tables. Same thing for OR. We have false, false, false. False, true, false. Wait, that's not right, is it? Yeah, those should be ones. Yep, you're absolutely correct. Must be it's a copy-paste error. So this one is false or true is true. True or false is true, and true or true is true. And then not is very simple because it's just one operator. Not 0 is 1. Not 1 is 0. Right? Very good. All right, now if we were to go into some of the expressions that we saw earlier where we have multiple variables, what happens to our table? It gets super big, right? So in this case, we have two variables, each with two options. So it's 2 to the second. So how many rows do I have? 2 squared is 4, right? But now if I go into 3 variables, each with 2 options, how many rows do I have? No, it'd be 8, right? 2 to the, or sorry, 3 squared. Wait. It should be 8. Oh yeah, it's 2 to the n. Sorry, it's not. Yeah, it's 2 to the n. Yeah, it's 8 is the answer. All right, so now let's go into numbers. All right, so we're going to get a little abstract here for a second. Okay, when you guys first, in like way back in the day, when you guys were learning about numbers in kindergarten or preschool or whatever, we were taught that digits are placeholders for numerical value. What do I mean by a digit? What's a digit? Madison, what's a digit?
Single number to represent big things.
Yeah, single number. Like 9 is a digit, right? But what does 9 actually mean? It means 9 things, right? 9 ones in this case, right? Very good. So our digits are combined into groups to create larger numbers. For example, 1982 has 4 digits. Simple way to think of numbers is that digits are organized into columns. And this is really how we do it in our base 10, right? We have thousands, hundreds, tens, and ones. So if you add this all up, you have 1,000, you 982 for 1982, right? Very simple. You guys just do that in your head automatically. Base 10 is awesome because, right, you can just add zeros at the end of things. It's super easy. But it still follows a pattern of how to do a numerical system, right? So our base 10 numbers really fall into this, right? Our thousands is really 10 to the third, hundreds is 10 to the second, tens is 10 to the 1, and your 10 to the 0 is just your digits, or your final count, right? So instead of, right, whereas here we said it was 1 times 1,000, plus 9 times 100, plus 8 times 10, plus 2 times 1, what we're really doing is we're going 1 times 10 to the third, plus 9 times 10 to the second, plus 8 times 10 to the first, plus 2 times 10 to the 0. What's 10 to the 0? 1, right? All right, so binary system, which is a base 2, works exactly the same way, except that it's not base 10, it's base 2. All right, so instead of digits representing powers of 10, they represent powers of 2. So what this means is if we were to express the number 2, it would be 2 to the 1 plus 2 to the 0, which is what? 1 times 2 to the 1, which is what? 1 times 2 to the 0 is how much? No, sorry. 1 times 2 to the 1 is how much? 2 plus 0 times 2 to the 0, 0. So what do we get? 2. 2 plus 0 is 2. Right? So again, let's go through that, right? So we have our columns just the same. So 2 to the 1, we have 1 of those. So we have 1, 2. And we have 0 ones, which equals 2. What happens when we get larger than a 2? What's going to happen? We pop over to the next column, and then the next column, then the next column. Okay, can you have anything on a base 2 system, can you have anything larger than a 1 or a 0 in your columns? Why is that? Because what automatically fill to the next column, right? What is 2 times 2 to the 0? It's 2, but then it falls into the next column. It makes sense. All right, so we express the number 3 as 1, 2 to the 1 plus 1, 2 to the 0, which is 2 plus 1 equals 3. But now when we hit 4, we go over to populate this other column because 2 to the 2 is how much? 4. So we have 1, 4, 0, 2s, 0, 1s equals 4. Make sense? So if we were to plot binary, or not plot, but if we were to put side by side binary versus decimal, what you end up forming, because remember our 1s are using our digits places, right? Whereas before we had 1,982, where we had a 1, a 9, an 8, and a 2. Now we only have 1s and 0s to fill in our spots. So what we see here is that 0 equals 0. We love that one. That's super easy. 1 equals 1. We're all over that one. But binary is 1, 0. 1, 2, and 0, 1s. 3 is 1, 1. 1, 2, and 1, 1. 4 is 1, 4. 0, 2s, and 0, 1s. And so on and so on. Eventually we get to 12, which is 1, 1, 0, 0. And so on, and so on, and so on. All right, the easiest way to do this is to draw your columns, put your exponents in there, and then just sum up your math, okay? So let's do some of these together on page 50 in your book. Okay, so what we have first is we have 1, 1, 0, 1. How much is that in decimal, which is base 10? Okay, so what's the first? So we have 4 digits there. So we start from the right this time. I'm on my side, so we'll do it from your side, right? So we start from the right. What's the first digit being the 1 on the right side? How much is that? That's 2 to the what? 0. So I have 1, 2 to the 0, which is how much? 1. And then I have 0, so it doesn't matter. And then I have 1, 2 to the what? 2 to the 2, so it's 1, 4. And then I have 1, 2 to the what? Third, which is how much? 8. So very good. So I have an 8 plus a 4 plus a 0 plus a 1. So what does that number equal? What's that? 13. Is that what I got? That's what I got, 13. Question? Yes, sir. All right. So no, that's completely fair. So for those who are confused, again, let's go back and look at our grid here, right? So in this case, we have another 1 over here, right? So we had 1, 1, 0, 1 was our number. So I have 1, 2 to the 0. I have 0, 2 to the 1s. I have 1, 2 to the second, and I have 1, 2 to the third, which is over here. Yes?
Where do you get the second, first, and 0th power for each one?
Because that's what each digit represents.
How is that for each?
Right, so again, let's go back to our decimal, right? The 2 in 1982 is really just saying you have 2 of 10 to the 0. Because 10 to the 0 is what again? 1. So I have 2 1s, so I have a value of what there? 2 1s is? 2 1s is 2. 2 times 1 is 2, right? And then I have 8 times 10 to the first, which is what?
No.
80. 80, right? So what you're doing is you're just adding these up as you go, right? That's the same way that you're doing them. It's just that you do it automatically in your head on base 10 because that's how you've grown up, right? But we're doing the same thing with binary, and we're just forming this grid here, and it'll keep going out, right, more and more. But we're forming this grid here. So our last number was 1, 1, 0, 1. So 2 to the third has a value of what? 8, and we had 1, 8. And we had 1, 2 to the second. What's 2 to the second? 4. So we have 8, 4. We had a 0 here, so that's worth 0. And now we had a 1 here, which is what's 2 to the 0? 1. So we had 1, 1. So we have 8, 4, 0, and 1, which adds up to what? 13. Very good.
So where did 2 come from out of all of that?
Because it's a base 2 system. That's just how it works, right? So that's why we had the 10s up there, because it's a base 10 system. And this is binary. That's where your 2s are coming from. All right. So who has, in the meantime, done B and want to take a crack at number B, which is 10101? What do we think? I hear a 21 in the front. I hear a 21 in the back. I hear a lot of nods for 21. All right, so I think that's very good. So I have 1 times 2 to the fourth, 0, 2 to the third, 1, 2 to the second, 0, 2 to the first, 1, 2 to the 0, which is 16 plus 0 plus 4 plus 0 plus 1 equals 21. All right, and I know I heard some people, at least in the front, working on C, which is 11101. What did we get for that one? 61, emphatically. I love it. All right. 32 plus 16 plus 8 plus 4 plus 0 plus 1 equals 61. All right. So here's the money question. This is stupid. Why binary? Okay. So for sure, expressing large numbers in binary is very cumbersome, right? So let me ask you this, okay? Aside from the fact that it's because it's how computers work, let me ask you, why is this how computers work?
On and off switches.
On and off switches, okay? Why do you think?
Because computers can only do on state, off state.
On state and off state? Okay. So I like to propose this example to you. Is anybody here a Boy Scout or a Girl Scout? You're a Boy Scout? You were at one point, Cub Scout, something? Okay, so I throw you in the middle, so I blindfold you. I spin you around a couple times, and I throw you in the middle of the woods. Okay? What time is it? How are you going to tell me what time it is?
Using your logic.
Using your logic? I don't think that's going to work in the woods.
There's no way.
So the answer is you're going to look at the sun, right?
Yeah, but you're spun in a random direction.
What's that? Oh, yeah, sorry. I removed the blindfold. All right. Fair enough. I removed the blind. Yes, you're right. Fair enough. I removed the blindfold. How are you going to tell what time it is? Look at the sun. All right. And you can probably be pretty accurate on that, right? So you're not going to look directly at the sun because we're not 5, right? But you're going to look at the sun. You're going to say, all right, it's about over there. So it's probably in the afternoon, or it's probably in the morning. Are you going to be able to tell me when it's 11:15? Can you tell me when it's noon-ish? Can you tell me when it's afternoon or morning? A lot easier, right? And what you can do very easily is tell me what? Whether it's day or night. Right? So instead of in a computer, let's say we wanted to get out of a computer digits 1 through 10. What we would have to do is we would have to send voltages in varying degrees and have the computer have to detect voltages and put them in that range. Instead, just like Lynn said, we can instead use a switch, which is on or off. It's very easy to detect day or night. It's very easy to detect on or off. It's a lot harder for you to tell me whether it's exactly 11:15, and it would be just as hard for a computer to say, well, I'm getting exactly 3.8 millivolts, so that must be about a 3 or a 4, right? So instead, we just say day or night, true or false, 1 or 0, open or closed. And remind me from a switch, if my switch is open, do I have current? No, my switch is open, so I have no current, which means my light is what? Off. Very, very, very good. All right, so does that analogy make a little more clear on why we actually care about binary, aside from the fact that I'm up here talking about it, right? All right, so this analogy highlights exactly why binary is used in modern electronics. We just kind of talked through it, right? It's really just switches, okay? But the cool thing about this from a computer standpoint is that if we need to create larger and larger numbers, all we need to do is add more and more and more circuits. And that's why the smarter that computers have become over the years, they've added more and more transistors, they've added more and more switches, and so that they can compute more things at the same time. They can go on and off faster, create groups, and work together. Okay? So, again, we already have discussed the switch. That's why I asked for the reminder about the on or off. But it only has two states, which is on or off. And this two-state open-closed is, of course, why we use, or is why binary works in the computer, right? So all we have to do now in the computer for 1 or 0 is either measure, do I have current? Do I not have current? Do I have voltage? Do I not have voltage? That's all you really need to measure, instead of trying to figure out how much or how it goes, right? So a computer, when it boils down to it, is nothing more than this little tiny piece of silicon with billions and billions of connected switches on it. That's all it is. Now they're wired and they're configured in a way that some of them turn each other on and off, and they work together. But fundamentally, all they are is a bunch of switches. Okay? And that switch is a transistor, right? The actual switches that we use are very different, of course, than the mechanical light switches that you hit when you're in a room. They're called transistors, and these are called solid-state devices because they have no moving parts. There's not actually a switch that opens and closes, right? And you can think about that if you think back to pictures you might have seen of like the early day computers. They were the size of this room. And why were they the size of this room? Because they literally had to have switches that could move. They had to have vacuum tubes, right? They had to have a big amount of stuff. I actually have a picture that I show when I go out on my high school recruiting trips. I actually show a picture of an old 5 megabyte drive being loaded by a forklift onto a Pan American airline, which became like Delta. I don't even know. It may became American. Either way, Pan American Airlines back in the day, it's being loaded by a forklift. 5 megabyte drive, right? You guys probably have 5 megabytes in your hat these days. I don't know, right? So, all right. So, the faster that these, really, the majority of the progress that we've made in this century and the last has been due to our improvements on making the switches faster, smaller, and how many of them we can pack in a given area. Okay, the faster the switches are able to turn on and off dictate the speed of the computer. And the smaller they are, the computer either can be smaller or smarter by packing more switches into it. And that's what, who's heard of Moore's Law? Right? Moore's Law fundamentally dictates that every 2 years we're going to roughly double the amount of transistors on a chip. Right? And that's held up for a long time, and we continue to pound and try to execute to that, right? The reason you want to do that is twofold. You can either take the same chip and basically put twice as many switches on it, making it smarter, or you can take the same number of switches and put them into a smaller space, which then enables you to not have a 5 megabyte drive that needs to be flown across the country, but instead a 5 terabyte drive that you can have sitting on your desktop. Right. Okay? So, if we were to go down to page 51 and look at an actual circuit, what is the number being represented by this circuit? And I'll let you guys do this one on your own. So somebody remind me, a closed switch has a value of what? And why is it a value of 1? Because I'm getting current, right? And an open switch has no current, so it has a value of what? 0. Very good. All right, so what number is being represented by this circuit? All right, who's got an answer for me? Who wants to be brave? J-Rom's going to be brave? What do you have?
I got 50. Yeah, I don't know if it's right.
You have 50, 50?
58.
58? We get other numbers, 58? What do you have, Benjamin? 144? What do you have, Thomas? 154?
Ooh, that's close enough.
Close enough is not good enough.
No, that's it's
All right.
I gotta check my math.
So,
Is it not
I like Thomas's answer, but let's see how it comes out. All right. So we have the number, because of the switches, we have 1, 0, 0, 1, 1, 0, 1, 0. So what's that first one represent? The one on the far left. What is that one worth? What's that? No, the one on the far left. Your left. So I got 1 times 2 to the 7th, which is 128, plus 16, plus 8, plus 2, and we get 154. Nicely done, sir. Good job. All right, so let's talk a bit about our engineering application for the evening. Okay? The second basic function of the transistor is a switch within a digital circuit. In this role, the transistor serves as a fundamental building block of modern digital devices. Because the focus of this chapter is on computers, or this lecture is on computers, remember I'm pulling this from my book, we will thus limit our discussion of the function of the transistor as a switch. Fundamentally, these are 3-terminal devices, and I'll show this in a second. So there are currently 2 common types of transistors, each of which have slightly differences in how they're constructed. What we're going to show tonight is what's called the MOSFET, or the metal oxide semiconductor field effect transistor. Yeah, make sure you memorize that for the quiz later, okay? All right, but almost all transistors that are manufactured today from a computing standpoint are similar in design to the MOSFET, right? So that's what we're going to be talking about. I'm going to show pictures of, okay? So fundamentally, a transistor is composed of semiconductors. Semiconductors, which also live in the middle of the periodic table, right, are materials that have properties between those of a conductor and an insulator. They can be both, or they can be either. Okay? Pure silicon, which is what all chips are made of, is an insulator, as very little electricity flows through it. So if it's an insulator and it doesn't flow, why the heck do we build transistors on it? Any ideas? Why? So it can block the current? Okay. Okay. You're right. The answer is that we want it built on something that won't transmit, because what would happen if we tried to build our circuit on like metal? Yeah, exactly. It's gonna get out and nothing's gonna work, right? Okay. But what we can do is through a process called doping, right, which is different than like what Lance Armstrong did, okay? But through a process called doping, small amounts of other elements, particularly boron and phosphorus, are typically the ones we use, can be added into the silicon, resulting in a change to electrical conductivity of the material. So somebody remind me, because I forget, looking at the periodic table, what is the charge on silicon? It's 4. Silicon is 4. That's very good. So right next to it, so silicon is number 14 up there. Okay? One of the ones we use for doping is boron, which is number 5. Where is boron in relation to silicon on the periodic table? It's 1 up and 1 over. You're correct. So what does being 1 over, why might being 1 over, and to be clear, it's 1 over to the left. What's the charge on boron? 3. Okay? And now phosphorus is our other one. What's the charge on phosphorus? Phosphorus is literally right next to silicon, so number 15. All right, so we agree, though, that we have one of these that is just to the left, meaning it has a slightly negative charge. And we have one to the right, which means it has a, sorry, I did it the other way. Boron will dope for which direction? So boron has a deficiency of valence electrons, right? It has how many valence electrons? 3. No, it is 3. I promise you it's 3, right? Phosphorus has how many valence electrons? 5. Okay, so what would happen? Let's just cheat and go to the next slide. Okay? So what we have here is we have a silicon lattice. Pure silicon. All these guys are bound to each other. The 4s are bound to other 4s, so what do I have? A completely neutral material. What happens now if I introduce the phosphorus, which has how many valence electrons again? 5. What happens if I put a phosphorus inside of this lattice? I have an extra electron just sitting here. So what's the overall charge now of this? It has an extra electron, so it's what? Negative. So we call this N-type silicon, right? And I realize it can be inherently backwards to think about it that way, that adding more makes it negative. But remember, it's adding more electrons, right? And on the flip side, in P-type silicon, or positive type silicon, right, we've added boron, which remind me, how many valence does boron have? 3. So if I put it into this material that is electrically stable at 4, what do I now have? I'm missing an electron. Yes, sir?
Is this where NPN and
That is exactly correct. Yes. NPN and PNP. That's exactly where this has come from. Okay? So, and what he's asking for is making, like, he's going towards building a transistor and making diodes. Right? That's what we're doing. Right? Do you have, is that what you're talking about from a diode? You have like an NPN diode or a PNP diode, right? Yeah. All right, so what we do is we put these together like this. Okay, so this is a cross-section of a MOSFET or of a metal oxide semiconductor transistor. So what we have is we have a gate. This gate here is where we will apply some sort of voltage. We have the source and the drain. The source and the drain are really just wires. So what we want to do is think about this as a wire applying, right? Let's say we have current that wants to go here and out. Okay? So this consists of, obviously it's all one piece of silicon, but what they've done is they've patterned it accordingly that there's essentially a hole of N and a hole of P-type, right? What they did is they covered up part of it, they shot in phosphorus in one point, they covered it all up again, they exposed another point, they bombarded it with boron on the other part to make it negative, and we now have 2 little wells, that they call them, of P-type and N-type, okay? So what happens is the gate itself has extremely low conductivity here. So this oxide insulator means that this guy and this guy don't interact. And that's important. So what we see here is, so remember these guys here have different charges, right? Our N-type has what type of charge? Negative. So I drew it with little blue negatives. So we have our N's here. And we have our P-type, which is the rest here. So let's think about this. If I were to now have current that was flowing in here, would the current be able to get here, yes or no? So you were going for your PNP, or in this case, NPN, is essentially what we're forming here. If my electron is here, my electrons want to flow This way? Or no? Can they get there? No? Yes? What's that? Right. Remember, we have to have a continuous path. You have to have a continuous path for your electrons to be able to flow. So what we're going to do, and so right now, no, you're not getting flow. What you can do is, and check out this little animation here. Okay? What we do is if we apply a voltage to the gate, we actually push away, because we apply positive voltage to the gate, what happens to the other positives? They get pushed away. You essentially form a bridge of negative there, and now your electrons can flow through. Does that make sense? Yes, sir?
Wouldn't they want to go that direction already?
They want to go that direction. So you're talking up here?
Yeah, wouldn't they?
So you need a continuous, so you're correct. Negative wants to go to positive, right? Because why? Because the electrons want to go balance it out. But there's a problem here. Which direction do these guys want to go? Let's say there's an electron here. Which direction does this guy want to go? Wants to go out? Which direction does this guy want to go? Right, so do I have a continuous path? Because they're fighting against each other. Right. You have to have a continuous path. In has to equal out. If in doesn't equal out, what happens to our world? It doesn't make sense anymore, right? So the only way that we can get those to move across, the only way we can provide a way, because remember, if an electron comes in, an electron has to go out, right? We have to, or if an electron goes out, the other way to think about it is an electron has to come in. So by applying that and creating the bridge, our electrons can now fly across that bridge, and we now have current passing through that transistor. So what have we effectively done to this transistor by applying the voltage? What's that? We've opened it. Or yes. From a switch standpoint, yes, you've closed the switch. Correct. What was your question?
I was going to just ask, so right now there is no, like the electrons wouldn't actually move across the switch. They're just allowed to move across the switch.
So, well, yeah, but you're still applying a current.
Yeah, so the current that they
Right. Yeah, you're applying a current to your. So this is right. So your computer's on. You have power. You have current to your computer, right? And that switch is going to say yes or no, right? 1 or 0. Okay. What's cool about this is not only is electrical current now able to flow from the source to the drain, but I have to actually apply a voltage to that gate, right? So what if now this guy that's open goes and supplies another gate or another series of gates? Now I can open up a bunch more switches, right? So now you can see how these switches start to interplay, and all of a sudden you can hit the power button on your computer, and your computer hums to life, right? Say, all right, one switch gets open when you hit your power button on your computer or your phone or whatever, and all these other switches start to turn on in series, and they start opening and closing and talking to each other. Okay? So when we do it in this manner, a transistor is able to perform as a switch. When no voltage is present, the switch is off. But when we apply voltage, the switch is on, right? Or closed or open. So now that we understand how this works, we can begin to form a picture of how these can turn each other on and off. Connecting the output of one transistor to the input or to the gate of another transistor enables the first to operate the second. Doing it in this fashion, we can start to create logic circuits. Okay? And most integrated circuits or computer chips contain billion of these all connected together to form circuits. Any other questions before we move on? I thought I saw one more hand go up. Was it your question? Forgot it? Okay, fair enough. All right, next I want to talk real quick about bits and bytes. Okay, so in binary, we refer to each individual digit as a bit. This word is simply just a shortening of binary digit. So a bit is the smallest unit of information that can be stored or manipulated, containing only 1 or 2 values, 0 or 1. Individual bits are grouped together to allow for formation of larger numbers. Such the binary number 1010 has how many bits? 4. Because you have 4 slots of stored data. You have either a 1 or a 0. So I have 4 slots of stored data. It makes sense. No, I know you were going for what the number actually represented. But we have 4 bits here. Okay, so the total number of distinct values can be expressed by 2 to the n, where n is the number of bits that we have. Okay? So if I have 1 bit, I only have 2 combinations, 1 or 0. But if I have 4 bits, I have how many? 16, 2 to the 4th, right? I can do, well, I listed them all there, right? 0000, 0001, 0010, right? And so on. So in modern computers, bits are typically grouped together into 8-bit collection called a byte, right? 1 byte represents 8 bits. So with an 8-bit byte, we are able to represent 256, or 2 to the 8th, unique values ranging from 0 to 255. Why is 256 a very important number in computing? The answer is actually because of this. But who here's seen, man, maybe you guys, I don't know, I grew up when computers were still becoming a thing, right? 256 colors, VGA, right? Right? 256 is a thing because of 8, or because of the byte, right? Okay? So the space that data takes up in a computer is measured in bytes. Okay? Single byte is large enough to hold a single typed letter. Okay, so it takes, think about that, it takes 8 ones and zeros, or 8 spots of ones and zeros to represent a single letter. So every time you type a document that is, what was your last history report? Minimum 1,000 words or something like that, right? That should, by and large, correlate to so many bits, okay? All right, so how does a computer work? Aside from you turn it on and you operate it, okay? A computer is nothing more, doesn't matter whether it's your phone, whatever you want to call it, a computer is nothing more than something that takes input and creates output, okay? In your computer, what is an input unit on your computer? Keyboard. What else? Mouse. Touch screen, something like that, right? What is an output on your computer or phone?
Whatever happens.
Screen. Sounds, very good. Your speakers, right, is an output unit. Okay? So we are going to take some form of data and we're going to put it into our computer. That is going to go into the primary memory of your computer. And then there's the secondary memory, which can talk to the primary. But fundamentally, what drives your computer is this box here called the CPU. So what we have here are what we call registers. Does anybody know what the registers do in a computer? The best way to think of it, very simplistically, and again, I'm sure if somebody who actually was like a computer engineer was listening to this, they'd freak out, right? But the best way to think of your registers is it's a shelf where you can store things on, okay? Actually, it's the best one would be like one of those IKEA cubby things, you know, where they've got like so many cubbies. You can fill up the cubbies and someone on the other side can pull out of the cubbies, right? And it's a transition. Yes?
So would it be, that would be the place where the registers.
Yeah. Okay, and then we have the ALU. Does anybody know what that stands for? Yeah, it's hard to say, but yes, arithmetic logic unit, and then we have the control unit. All right, so we've gone through these, right? Input, convert instructions and information, aka your keyboard or your mouse. Memory or storage dictates how much information can permanently be stored. Most computers have an internal form of secondary memory, such as a hard drive, which is usually a form of magnetic memory. Smaller devices such as cameras, like the one we're recording on, and cell phones utilize other storage solutions such as like flash memories. Okay? Information is processed in the CPU and using primary memory. So both a fast CPU and an ample amount of primary storage are necessary for a fast computer. The output devices, like again your monitor, convert the digital data produced into a form that we can understand. Right? You can't look into the computer and say, oh, I see exactly what switches are on and off and do anything with it. Right? Printer, for example, makes a permanent form of output, but your screen makes an ongoing form of output. So I want to talk real quick about digital graphics and how this works. So the computer screen, which is your output, one of your outputs, or the electronic visual display is obviously the most commonly used output on your computer. This display serves as an interface between the users and the computer, allowing for visual control. A display has hundreds of thousands of tiny squares arranged in rows and columns. So if I have like 1080p, what does 1080p mean?
It's 1080 pixels tall by 19, well, typically.
Yes, you're correct. It's 10,080 pixels tall by 1920 wide. That is pretty much the standard these days for like YouTube and stuff like that. Yes.
How do you know 1920 wide?
It's just the way it is. I don't know why it's not 1920p. It's just 1080p is what they call it. It's just the way it is. But it's 1820 by older resolutions. You may see 800 by 600. That was the way it used to be. 800 by 600 used to be the.
So how does the name correspond with both the length of like height and width?
1080p. It's just knowing that. Go ahead. Right.
So most modern displays are 16 by 9. So if it's 1080p, then if you do the ratio, then that puts out to 1920.
Right. Yeah. Yeah, you're exactly correct. Much better said, right? So resolution, what we're talking about, is expressed in the form of AXB, right? So in this case, 1920 by 1080, which is just abbreviated 1080p, okay? Where A identifies pixels on the horizontal and B denotes pixels on the vertical. So a display with 800 by 600, which is like the old school, thus contains 480,000 pixels, 800 by 600, right? So how many pixels would be in a 1920 by 1080? I don't know, but it's a lot more than 48,000. I mean, we can multiply it and figure it out, right? We're all smart. All right, but if you were to, I actually did this, right? And look how humorous I am because I used the word pixel to do it, right? If you actually go in and blow up an image, this is what it will actually look like, right? So the X, you see that it's got black in the middle, it's got some kind of grays on the edge. The computer is representing the X with this image, right? You're not looking at an X. What you're looking at is some field of squares that are on and off or in various colors to make it. Okay? So fundamentally, a digital graphic is just a collection of millions of individual pixels arranged in a grid pattern. So let's say, in this case, we're only going to use ones and zeros. One being what? One being on, and zero being off. What do you think, what color do you think on represents? You're correct. White. Why is it white?
Because the computer screens are normally.
Yeah, when you shut your computer screen off, what color is it? It's black. Right? But yes, white is technically the presence of all colors, right? And black is the absence of all colors, right? All right. So in this digital image that I'm showing up here, which is a very crudely drawn smiley face because I didn't want to put ones and zeros in for the rest of my life in a 1080p, right? What we see, and I highlighted in blue just so you can see them, the eyes are zeros, and the smile are zeros, and the rest of the screen is lit up, okay? Now if I had a black, and then you wouldn't be able to see the grid, but if I had black and the eyes were white and the smiley face was white, and it was a black smiley face, whatever, it would be the other way around. Okay? So this raster image is a two-dimensional array which not only includes the value of the cell, but it also has to include the location of the cell. So let's start thinking about this in terms of bits and bytes. Okay? A location is going to have a certain number of digits because it's going to have some height digits, some width digits, or that'd be width and then height, and then it's going to have some color code associated with it. Right? That color code in of itself, if it's black or white, is just 1 or 0. But what if now we are in, I don't even know how many colors are possible these days. It's a lot. Has anybody done any internet programming? We're using like the hex code colors. Like, you know, it's usually like pound FFA0, something like that, right? That is a long string of numbers, right? So now we start thinking about actually making an image and why a picture file might be so large, right, in the megabytes, is because you just have this file full of just numbers saying these numbers correspond to this cell, for lack of a better term, these numbers correspond to this cell, and this cell must be this color. And you have to identify all of the cells within the entire picture to make it. And then movie files, of course, become significantly larger. Why? Because you have to identify what color it's going to be at a given time, right? And that's why your files get exponentially large as we start to go from a document to a picture to a video, right? Sound is actually significantly easier because you're not doing visual stuff, right? But right, because your MP3s generally have a size of what, like 4 megs, something like that, right? Is a megabyte, or but a video is in like gigabytes, right? Okay. All right. Lastly, let's talk about the framework of a computer in hardware, software, and firmware. So the physical parts of the computer are referred to as hardware. Most of you guys know that. They can't really be changed out. You can go swap out a mouse or something like that, but you can't just like go swap out your hard drive on Tuesday, right? It can be done, but it's probably not something that you're going to do very frequently. The flexibility of the computer is not from how it's made. It's not from the hardware. It comes from the programs. Okay? Computer programs can be easily varied, and they're thus referred to as software. Hardware is useless without software. But of course, without hardware, the software has nothing to run on, right? There's no switches for it to run on. Okay? So computer's hardware is what makes it powerful, but the ability to run different software is what makes it actually usable to us. So the castle of, I don't know, it's kind of a castle, whatever you want to call it, right? But the way that a computer works is it's all based on the hardware, right? What's my hard drive look like? What's my memory look like? What do I have? And on top of that is the BIOS. What's BIOS? What is it? The basic input-output system, right? And that's basically the what happens if I press the A key, right? That's hard-coded into your computer, right? There's no program that you have to boot up. Well, that's not technically correct. There is a program you have to boot up, but it's actually written into the hardware of your computer, right? Because when you turn on your computer, what's it do first? If you look at it, usually when you turn on your computer, one of the first things you'll see, like on the black screen up in the like little white, it'll be like initiating BIOS, right? Because you have to know if I hit F4 or whatever at the beginning when your computer's kicking on, it has to know what that means. Or is it F4, F3, F2, whatever it is that goes you into the DOS-looking thing, right? Then we have the operating system. This is your Windows, your Android, whatever. This is what fundamentally talks between your computer's hardware and all of the apps that you want to use. Right? And an app doesn't have to be something just as catchy as, you know, I don't know, whatever app you have, Angry Birds, or is that what you're saying, Angry Birds? Fair enough, right? Yeah, so there's Angry Birds, there's Fortnite, Destiny, whatever you guys have, right? These are all the programs that we add and delete like crazy. But they all fundamentally talk to the OS, which then talks to the rest of the computer. Okay? And then I'm like accumulating these things up here. All right. Application software, software types, applications based on a specific purpose, the operating system we already talked about, and then the basic input-output system. This is fascinating. I actually was talking to some other Intel engineers who didn't know what I did, and I didn't know what they did, and we were talking at a bar one time. And they were BIOS engineers, and they're basically like golden people who are protected at all times, and they never get to leave campus or something, right? But so when the computers first turned on, as we know, the machine completes several automatic internal processes. Process is controlled by a specific set of software that's embedded on the core of the computer called the BIOS. Has anybody ever done a BIOS update on their computer? What does it basically do to your computer? Turns your computer into a rock for like 8 hours, right? Your computer is completely unusable, right? So it's very difficult to do. It's very rare that you have a BIOS update. There usually has to be something significantly wrong with your computer. Intel was in the news like well, I don't know, it was 3-4 years ago at this point. They had an issue with one of the chips where there was a security flaw and they had to push a BIOS update, right? They had to fundamentally change the way that it interacts with the hardware, okay? So although this is truly a set of digital program instructions, because it's simultaneously poured on one of the computer's main chips, it's actually considered to be firmware, right? It is not an app. It is not software. It's considered what's called firmware. All right, any questions? I know we blitzed through that real quick. Yes, sir?
What is firmware?
Firmware is computer software that is embedded on the computer itself.
Oh, so it comes.
Well, I mean, your OS and programs technically come with your computer when you buy it, but it's below the operating system.
So like basic functions of that computer.
Correct. Like again, like the best example I can come up with is when I hit the A key, what does that do? Right? Like the BIOS says like, oh, JRAM hit the A key, so he wants me to type A, and then it sends whatever the code for A is, 100. It's I don't know what it is off the top of my head, right? But whatever the code for A is gets sent, gets stored in one of the registers, and then it gets put into your word processing program. Okay. Yes, sir. RAM and actual memory. So random access memory fundamentally is not permanent memory. Okay, it's memory that's being used to process what you're actually doing at the time. And then if you go and you write something to like a hard drive, that's when it like puts the ones and zeros in a more permanent position. Right? RAM is constantly moving back and forth, pushing in the registers, putting it to the CPU and processing it, right? Does that make sense? And that's why like a high RAM, for those of you guys who play computer games, right, you want a high RAM because you need to constantly be processing that information. It doesn't really matter for the guys playing computer games how much storage you have because you're not storing anything at the time, right? Whereas those of us who are like doing files and stuff, we may need low RAM. Like my work laptop has exceedingly absurdly low RAM, but decent memory, right? You're gonna ask a question? Oh, okay. Okay. Anything else? All right, let's take a quick break. We'll come back, run through biomaterials, and we'll get you guys out of here.